This is a video about uniform circular motion. Please watch the animation first and then take your notes after the animation. Let's look at the simulation of an object undergoing uniform circular motion. Notice that the velocity vector's length remains constant. That means the speed is constant, but the direction continues to change. Now, if we look at two different locations where we observe the velocities, the change in the velocities of those two different values is what we call the acceleration. This velocity vector always points inward. Since we know the change in velocity is the acceleration, therefore the acceleration is what's always pointing inward. Notice the velocity always points tangential to the path, but the acceleration always points inward. Great, so you've watched the animation. And so now we can talk about uniform circular motion. An object that moves at uniform speed in a circle of constant radius is said to be in uniform circular motion. Why is uniform circular motion considered accelerated motion? Well, as you saw in the video, although the speed is constant, the velocity is not constant since the object is in uniform circular motion is continually changing direction. Centripetal acceleration, or center-seeking acceleration, points toward the center of the circle and keeps an object moving in circular motion. This type of acceleration is at right angles to the velocity, and this type of acceleration doesn't speed up the object or slow it down, it just turns it. Now remember, the velocity is tangential. It's tangent to the circle. And the equation is 2 pi r over t. So it comes from our average velocity equation, where x would be the distance that it goes around, and t would be the time that it would take to go around. We just capitalize that and call that the period, and r would just be the radius. So v is a tangential speed in meters per second, r is a radius in meters, and t is a period in seconds. The period is the time it takes to go around once. That takes us to the frequency equation. The frequency equation is simply 1 over the period, and the frequency's units are hertz, or 1 over seconds. The frequency is simply how many times around the circle an object goes every second. Now this is the equation for centripetal acceleration. The units are in meters per second squared, and v stands for the tangential speed in meters per second, and r is a radius in meters. And remember, the centripetal acceleration always points toward the center of the circle. A force responsible for inward acceleration is referred to as centripetal force. Centripetal force is simply the mass times the centripetal acceleration. So notice this is Newton's second law, and all we've done is replace acceleration with centripetal acceleration. Well, remember that the equation for centripetal acceleration is v squared over r. So all we have to do is replace the centripetal acceleration with v squared over r, and here is Newton's second law for uniform circular motion, where F stands for the centripetal force, V stands for the tangential speed in meters per second, and R is a radius in meters. And the centripetal force, just like the centripetal acceleration, always points toward the center of the circle. Newton's second law says it has to because the force, according to Newton's second law, always has a point in the same direction as acceleration. Now, let's look at the directions of uniform circular motion. Well, let's look at some topics. The velocity is always tangential. It always changes direction, but it's tangential to the circle. The speed is constant. It's only a magnitude, so there's no direction for the speed. The acceleration is always inward, as is the force. It's always inward as well. Now, any force can be centripetal. The name centripetal can be applied to any force in situations when the force is causing an object to move in a circle. You can identify the real force or combination of forces which are causing the centripetal acceleration. Again, any kind of force can act as a centripetal force. So let's look at some examples. This first example is a car that makes a turn on a flat road. What's the real identity of centripetal force in this situation? Well, it's the static friction. Another example is a weight that's tied to a string that's spun horizontally in a circle. What is the real identity of the centripetal force? In this case, it's tension. This is actually kind of a bad example because in the real situation, it wouldn't be a flat horizontal circle. But if it was in a horizontal circle, the centripetal force would be tension. As the moon orbits the Earth, what's the real identity of the centripetal force? Well, that's gravity, and that would be true for any satellite going around any other large body. As a race car turns on a bank curve on a racing track, what's the real identity of the centripetal force? Well, it's a normal force with some help from static friction. As you swing a mace in a vertical circle, what is the true identity of the centripetal force? In this case, it's tension with some help from gravity. When you're riding, for example, the Tennessee tornado at Dollywood, what's the real identity of centripetal force when you're in a vertical loop? In this case, it's gravity with some help from the normal force. The gravitron ride, what's the real centripetal force in this case? It's the normal force. For a real ball and a string, because remember earlier I said that when a ball is going in a horizontal circle, the centripetal force is due to tension, but a real ball on the string is a little more complicated, as is a frictionless bank curve. For those, we'll look at those examples in class. Now what I'd like for you to do is watch a couple videos with respect to uniform circular motion. Hey, this is Mr. Clarion. We're going to show you a quick little video here about how to find the direction of acceleration for a object undergoing uniform circular motion. So what I've got here is a Pasco accelerometer. So notice the little lights blink on depending on the direction of acceleration. Okay, so what I'm going to do is I'm going to take it and I'm going to attach it to this rotating platform just like this, and I'm going to spin it around. Okay, and when I spin it around, it's going to light up in the direction of the acceleration. And notice the red lights go on showing that the acceleration is inward. I'm going to spin it the other way, and notice that the red lights still stay on showing that the direction of acceleration is still inward. I'm going to move it to the other side. I'm going to move it to the other side, and let's look at where the acceleration is now. Okay, now the green lights go on, but the acceleration is still inward. Okay, so what does this prove, boys and girls? It proves that for centripetal acceleration, the direction is always inward. Mr. Clarion with a centripetal force demonstration. I've got a little centripetal force apparatus here, a little string with just a little platform on it. I got like a little Renews-It bottle. I'm going to put it right there. I'm going to take it like this, and I'm going to use centripetal force. It's my little centripetal force demonstration to show that centripetal force is always pulling inward. There you go. I didn't break it. I can even go over my head if I want to. Woo! How exciting is that? And then it safely comes to a stop.